We've let our gel sit for a while so that it would cool, and as it cools, it solidifies. Notice how it's now opaque. In other words, it looks sort of pinkish and less see-through than it was when it was a melted liquid. I can remove the gel boat from the gel casting tray, and because this is now solid, I can easily pull the comb out from the gel. I'm doing this very slowly, so that now there are wells. These are holes in the agarose matrix that don't go all the way through to the bottom. They're just pockets. That's why we call them wells. So what we're going to do with these is we're going to show you how to prepare this for electrophoresis. So I've got these electrodes here. I'm going to hook them up to the high power voltage supply over here. We would, if we were going to run this fully, we would fill this up with the 1X-TAE, the tris acetic acid and EDTA buffer. Tris is a buffer so that as we run the electricity through it, the pH doesn't change. The acetic acid and the EDTA make sure that there's the right salt concentrations and that there aren't heavy metal ions that are getting onto your DNA and breaking it, for example, for the electricity to flow clearly through this liquid. This right here is called a gel submersible, okay, a mini sub they sometimes call them, and we're putting our boat into the submersible, and then we fill this with the EDTA all the way over the gel, so it's completely submerged. After we've done that, we can get ready to add our samples and hook up the submersible to our power supply. So red is always positive, black is negative, DNA is negatively charged. So we want to make sure that when we're setting these things up, the red is where the wells are, so that we have I think I had it right the first time. Okay, so we have negatively charged DNA that we'll put here. We want it to go towards the positive pole because DNA is negatively charged. It'll go towards the red. The black is negatively charged, so it will repel the DNA and that will move through. Now again, I'm not doing all the steps right now, but if this was completely submerged under the EDTA, it would now be time to add our DNA samples to the wells. And I'll just quickly remind you how that's done. Here's our PCR tube. Okay, you can see the PCR product. If you zoom in on how much liquid is in there, there's 25 microliters inside this very small tube that holds about 200 microliters. In order to be able to see that the DNA, that clear PCR product, has entered the well, we like to add a little bit of dye to it. Now this dye does not bind to DNA. It's called a loading dye. It's just so that we can see whether our PCR product is in the proper part of the gel before we turn the electricity on. So we get a very small amount of this loading buffer, just a couple microliters, and we can add it to the liquid, turning our PCR product blue. Now it's very easy for me to see how much PCR product, this blue liquid, is loaded into the gel. So I'm going to get a slightly larger pipette tip here. This micropipetter can take this whole volume at once. And so I'll take my PCR product into the micropipette tip, and then I'll load it into one of the wells. So again, this would be done, this would be completely underwater, and you can see that the blue is now filling that central well where I put my PCR product. So the DNA is down in that compartment of the agarose. This loading dye also, not only is it blue so that I can see that I've successfully loaded it, It also has a little bit of usually glycerol in it, which is a very dense liquid, which will help hold the DNA down in the bottom of the well, even while there's liquid over the top. So if I had the 1xTAE in here, my next step, this was completely submerged under the liquid that has all those ions in it floating around so the electricity will flow through the liquid. I would put on the lid, plug in the machine. This power supply, I can then I would adjust the voltage. Voltage is currently at 0. I could set it to what voltage I wanted to run it at. And if I were to hit the run button, we'd usually run this about 100 volts for an Agarose gel like this. So, I could pump this up to whatever number of voltage I wanted. I'd push the run button and the electricity would flow through. The negative charge would push the DNA away. The positive charge at this end would pull the DNA towards it. And small fragments of DNA would move very quickly through the gel. In about 20 to 40 minutes, the smallest fragments of DNA would have moved all the way through this gel. So when it's done, I come and push the stop button, take this out, and we then go image our gel with a gel documentation camera by putting it on a UV light or a blue light box. The red that is in the gel, remember the CyberSafe dye? That dye binds to the DNA, and our DNA will glow as separate bands. I'll post an example on our Moodle website for the Developmental Biology Lab, so you can see what a gel would look like after I'd run our PCR samples, not just one sample, but many samples on a gel, and separate them out by size, with the smaller fragments moving towards the bottom of the gel and the larger PCR products being closer up to the wells, because those longer pieces of DNA get tangled on the matrix of the agarose fibers. Great, thanks.